Hi, everybody, it's Professor Mitchell. We're continuing Chapter 9 today and looking at Section 9.2 on the hyperbola, which is another one of our conic sections. In this section, we will locate a hyperbola's vertices and foci, write equations of hyperbolas in standard form, graph hyperbolas centered at the origin and not centered at the origin, and finally solve applied problems involving hyperbolas. So a hyperbola is the set of points in a plane, the difference of whose distances from two fixed points is constant. So the difference between this definition and the definition of an ellipse is the word difference. For an ellipse, that word was sum. So here is a GIF I found. And again, the idea is that if you subtract no matter what point you're looking at on the hyperbola, if you subtract the length of the smaller green line from the length of the longer green line, you're always going to get the same number. All right, the line through the foci intersects the hyperbola at 2 points called the vertices. The line segment that joins the vertices is called the transverse axis. And the midpoint of the transverse axis is the center of the hyperbola. So if you look at this picture, I think that the vertices in the center, at least, make a lot of sense. The foci are located out here. And just think of your transverse axis as being the line segment that cuts the parabola in half, but goes through the hyperbola. All right, the standard form of the equation of a hyperbola with center at the origin is either x squared over a squared minus y squared over b squared equals 1, or y squared over a squared minus x squared over b squared equals 1. In the first case, you get a hyperbola that intersects the x-axis, and in the second case, you get a hyperbola that intersects the y-axis. And the way that I remember which one is which is, again, I go back to intercepts. If you go to find the x and y intercepts of either one of these equations, take the first one, for example. If you were looking for x intercepts, you would set y equal to 0. And this term here, let me get my pen. This term here would disappear and would take the minus sign right along with it. So that would just leave you with x squared over a squared equals 1. And that's going to give you two x-intercepts at plus and minus a. On the other hand, and then if you try to find the y-intercepts for this equation by setting x equal to 0, this term will disappear. And what you'll be left with is negative y squared over b squared equals 1. That would give you y squared equals negative b squared, which has no real solutions. Okay, so the first type of hyperbola has two x-intercepts but no y-intercepts. And then you can do the same kind of thing with the other one. The other one is going to have two y-intercepts but no x-intercepts. The vertices are A units from the center, and the foci are C units from the center. Now, the number C does not figure into the equation of a hyperbola, so we need to know how C relates to A and B. So these equations are kind of similar to what we looked at in the last section, except notice they are a little different, the signs, S-I-G-N, of course. So for both equations, either b squared is equal to c squared minus a squared, or equivalently, c squared equals a squared plus b squared. All right, so in this example, we will find the vertices and locate the foci for the hyperbola with the equation x squared over 25 minus y squared over 16 equals 1. All right, so a squared is 25, which means a equals 5. So the vertices are negative 5, 0, and 5, 0. So this is going to be a sideways opening hyperbola. It intersects the x-axis. And then to find the foci, use the equation c squared equals a squared plus b squared. Putting in 25 for a squared and 16 for b squared, you get that c squared equals 41, which means c is the square root of 41. So the foci are at the points negative square root of 41, comma 0, and square root of 41, comma 0. All right, they did not ask me to graph this hyperbola, but there's the graph. Okay, so for the next example, we're going to find the vertices and locate the foci for the hyperbola with the equation y squared over 25 minus x squared over 16 equals 1. So just like in the last example, a squared equals 25, which means a equals 5. The difference this time is that the vertices are on the y-axis at 0, -5, and 0, 5. But just like before, when you go to find the value of c to find the foci, c will again come out to be the square root of 41. But of course, since the vertices are on the y-axis, the foci are also on the y-axis at 0, negative square root of 41, and 0, square root of 41. And there's the graph of that hyperbola. All right, in the next example, we'll find the standard form of the equation of a hyperbola with foci at 0, -5, and 0, 5, and vertices at 0, -3, and 0, 3. Because the foci are located at 0, -5, and 0, 5, the transverse axis lies on the y-axis. So this is an up and down opening hyperbola. So the form of the equation is y squared over a squared minus x squared over b squared equals 1. The distance from the center to either vertex is 3, which means a equals 3. The distance from the center to either focus is 5, which means c equals 5. So now we can use our equation to find the value of b. Since c squared equals a squared plus b squared, that means 25 equals 9 plus b squared, which means b squared is 16. So the equation of this hyperbola is y squared over 9 minus x squared over 16 equals 1. All right, so in order to start graphing our hyperbolas, see, intercepts don't tell the whole story. Let's say that I have this kind of hyperbola here, the kind I've been calling sideways opening. I can find the x-intercepts, but how do I know that the hyperbola looks like what you see pictured there and not, let's say, like this? All right, in other words, how do you know how wide or narrow the hyperbola is? So for that, you can use the asymptotes. Hyperbolas do have two slanted asymptotes. As x and y get larger, the two branches of the graph of a hyperbola approach a pair of intersecting straight lines called asymptotes. And of course, we've seen asymptotes with other kinds of graphs in previous chapters. They were always either horizontal or vertical, though. Okay, so these are called slant asymptotes. Sometimes they're called oblique asymptotes. Okay, let's see. So the hyperbola x squared over a squared minus y squared over b squared equals 1 has a horizontal transverse axis, as we talked about before, and it has two asymptotes, which are the lines y equals b over a x and also y equals negative b over a x. Okay, so that's for the sideways opening hyperbola. For the up and down opening hyperbola, y squared over a squared minus x squared over b squared equals 1. That has a vertical transverse axis, and its asymptotes are y equals a over b times x and y equals negative a over b times x. So you want to be, this is probably something that I would just have written down. I don't, unfortunately, have a great way of telling you how to remember this. All right, so this might be something to just put on your cheat sheet. Okay, so to graph a hyperbola, first we'll locate the vertices, and that's easy. Then we will use dashed lines to draw the rectangle centered at the origin with sides parallel to the axes, crossing one axis at plus or minus A and the other at plus or minus B. And then we'll use dashed lines to draw the diagonals of this rectangle and extend them to obtain the asymptote. So actually drawing this rectangle is a good way to help you remember how to draw the asymptotes. And then draw the two branches of the hyperbola by starting at each vertex and approaching the asymptotes. All right, so for example, let's graph and locate the foci of the hyperbola x squared over 36 minus y squared over 9 equals 1. And then we will find the equations of the asymptotes. All right, so first we'll locate the vertices. Since the equation has the form x squared over a squared minus y squared over b squared equals 1, that means a squared is 36 and b squared is 9. Since a squared is 36, that means a equals 6. And the vertices are on the x-axis at the points negative 6, 0 and 6, 0. All right, next we'll draw the rectangle. Since a squared is 36 and b squared is 9, that means a is 6 and b is 3. So the rectangle is going to pass through the points negative 6, 0 and 6, 0, which remember are the vertices, and also 0, negative 3 and 0, 3. All right, so you see how then you get the asymptotes. They just extend through the diagonals of that rectangle. So the extended diagonals of that rectangle have slopes 1/2 and negative 1/2. So the equations for the asymptotes are y equals 1/2 x and y equals negative 1/2 x. All right, and so step 4 is to draw the two branches of the hyperbola starting at each vertex and approaching the asymptotes, which you see done here. So as this hyperbola goes further and further away from the origin, it's going to get closer and closer to those lines. You find the foci the same way we did it before, using the equation c squared equals a squared plus b squared. That gives you c equals the square root of 45. And I just realized they could have simplified that radical, couldn't they? The square root of 45 simplifies to 3 square root of 5. So when you're doing your homework, just pay attention to how does it ask, does it ask for the radical to be simplified? It probably will. Okay, so they probably shouldn't have left this at square root of 45. They should have simplified it to 3 square root of 5. Okay, but for drawing the graph, it's okay to just ask the calculator what's a decimal that's close to square root of 45. So that would be 6.4. So if you're trying to plot the foci on your graph, that would look something like they're very, very close to the vertices. There's one right about there and one right about there. All right. Okay, so, oh, there, they did it on the next slide. And as we said before, the equations of the asymptotes are y equals 1/2 x and y equals negative 1/2 x. All right, so now we get into hyperbolas that are not centered at the origin, and I'm going to give you the same advice I gave you about ellipses. What I like to do is start off by pretending that the hyperbola is centered at the origin, and then the very last thing I do is shift everything, to the correct center, which has the form h comma k. All right, that's not exactly how they do it. All right, so your two different kinds of translated hyperbolas, right? Here's the sideways opening one. So when you replace x and y with x minus h and y minus k, it shifts the center to hk. And here's the one that opens up and down. Notice, all right, you want to be careful here. I think this has tripped me up once or twice. The minus k always goes next to the y, okay? All right, I probably should have done an example like this under ellipses, and I just didn't think to do it. So we'll do one for hyperbolas. We're going to graph the equation 4x squared minus 24x minus 9y squared minus 90y minus 153 equals 0. All right, so the way we're going to do that is by completing the square. Okay, so let me talk you through this. First, we're going to put our x terms together and put our y terms together, and we're also adding 153 to both sides, so the 153 ends up over here. Next, we're going to look at the coefficients of the x squared and y squared terms, which are 4 and -9, and we're going to factor those out. So easy for the 4, and we're leaving a space here for completing the square. Here we're factoring out a -9, which changes the sign of this term, right? The minus 90y becomes a plus 10y, right? Because we factored out a -9. All right, so it's been a little while since we've had to complete the square, so let's just talk through that. How they came up with the 9 here was you take -6. You know what? Let me get a text box for this. Put it right there. Take the -6 and divide it by 2. That gives you -3. And then square the -3. And that gives you 9. Okay, so that's how they came up with the 9. And then you do the same thing with the y. Take the 10, divide it by 2, which gives you 5. And then take the 5 and square it, and that gives you 25. All right, so now let me explain what's happening. Get my mouse back. All right, so we're adding a 9 here, and we're adding a 25 here. The reason that you see a plus 36 and a minus 225 over here is because by putting this 9 inside the parentheses, remember there's a 4 out here. So since I'm putting the 9 in parentheses, I really added 36 to this side of the equation. So I'm adding 36 to the other side of the equation to keep everything balanced. And then the same thing with the y, because there is a plus 25 here. Remember, there is a -9 over here. So what we really did there was we subtracted 225, and that's why I need the minus 225 over here to make up for that. Okay. All right, so we have completed the square. X squared minus 6x plus 9 is the same thing as x minus 3 squared. Y squared plus 10y plus 25 is the same thing as y plus 5 squared. And then the very last thing I'm going to do to put this in standard form, I want the number on the right-hand side to be a 1. So I am going to divide everybody by -36. And that is going to give me 4 over -36, which is -1/9. Here I'm going to have -9 over -36, which is plus 1/4. And over here I have a 1. So finally this thing is in standard form. So now we'll put the positive term in front, and we have y plus 5 squared over 4 minus x minus 3 squared over 9 equals 1. So again, the way that I would do this is I would start off by graphing the hyperbola y squared over 4 minus x squared over 9 equals 1. And then the very last thing I would do would be to shift it to its new center, which is 3, -5. Okay, so again, that's not exactly the way they do it, but Just wanted to mention that in case you find it easier like I do. So now we'll locate the vertices. A squared is 4, which means A is 2. So the vertices are A units above and below the center. And they've already gone ahead and found the center at 3, -5. That means the vertices are at 3, -3, and 3, -7. Next, we'll draw the rectangle. The rectangle passes through points that are 2 units above and below the center. So we found those points before. Those are the vertices. And it also passes through points that are 3 units to the right and left of the center. And that's because b squared is 9, right? Yeah, b squared is 9, this number right here. All right, so 3 units to the right of the center is the point 6, -5. 3 units to the left of the center is the point 0, -5. All right, so there's our rectangle. Next, we'll draw our asymptotes through the diagonals of the rectangle. The asymptotes for the unshifted hyperbola, so this is exactly the way I would do it, right? Pretending that the center is at the origin would be y equals plus or minus 2/3 x. The asymptotes for the shifted hyperbola are y plus 5 equals plus or minus 2/3 times x minus 3, all right? And you probably don't really need the equations of those lines. Really, all you need to do is draw them, and that's easy, right? Because they just go through the diagonals of the rectangle. Okay, so we'll skip over this. I don't think we need this. All right, so now we draw our hyperbola by starting at each vertex and approaching the asymptotes. And then the foci would be at the points 3, -5 minus c and 3, -5 plus c. We find the value of c the same way we did before. It turns out that c is the square root of 13. And so the foci are at the points 3, -5 plus or minus square root of 13. Okay. All right. So there we go. I think that's everything we need for that example. And that brings us to our application problem. I think this is such a fun problem. I remember the first time I showed this problem, there was one part of it that I had to stop and kind of scratch my head about. So I'll tell you about that part when we get there. An explosion is recorded by 2 microphones that are 2 miles apart. Microphone M1 receives the sound 3 seconds before microphone M2. Assuming sound travels at 1,100 feet per second, determine the possible locations of the explosion relative to the location of the microphones. So you can see a picture here. We're placing the microphones along the x-axis, equal distance, 1 mile away from the origin. All right, one is 1 mile to the right and the other one is 1 mile to the left. They are 2 miles apart. All right, so then we know that M1 received the sound 3 seconds before M2. Because sound, okay, so this next part I'm going to stop and explain a little bit, actually 2 parts of this. Because sound travels at 1,100 feet per second, actually I think I can do this with a text box. The difference between the distance from P to M1 and the distance from P to M2 is 3,300 feet. So that's using the equation distance equals rate times time. The rate is 1,100 feet per second. The time is 3 seconds, which gives you a distance of 3,300 feet. All right, so since the longer distance minus the shortest distance always comes out to 3,300 feet, that means that the set of possible points where this explosion could have occurred lie along a hyperbola. All right, so now let me get my mouse back here. Okay, so we'll use the standard form of the hyperbola's equation and the point x comma y, which we'll call the explosion point, lies on this hyperbola. So that hyperbola has equation x squared over a squared minus y squared over b squared equals 1. The differences between the distances is 3,300 feet. Thus, 2a is equal to 3,300, which means a is 1,650. So that was the thing that made me scratch my head the first time I saw this problem. I thought, okay, how did they get 2a equals 3,300? So I figured that out. So I'm going to switch over to my tablet where I have drawn a picture of that. Okay. So let's suppose for a moment that the explosion happened right here. It could have happened here. This is one of the points on the hyperbola. Remember that the differences between the distances to the two microphones comes out to 3,300. So in terms of A, which goes with the vertex of the hyperbola, you see one distance. The longer distance is 5,280 plus A, and the shorter distance is 5,280 minus A. The difference between those two distances is 3,300, so that gives you the equation you see on the right-hand side. Simplifying that equation, you get 5,280 plus A minus 5,280 plus A equals 3,300, and that's how you get your 2A equals 3,300, which means A is 1,650. All right, so going back to the PowerPoint. So now we know A is 1,650. So the equation of the hyperbola has this form, or if you actually square out the 1650, you get this. So now all we have to do is figure out B, and we're going to do that by using the foci. The distance from the center to either focus is 5,280, which means C is 5,280. So using the equation C squared equals A squared plus B squared, we get that B squared is equal to 25,155,900. So the equation of the hyperbola with a microphone at each focus is x squared over 2,722,500 minus y squared over 25,155,900 equals 1. We can conclude that the explosion occurred somewhere on the right branch of the hyperbola given by this equation. And that's going to do it for section 9.2. We'll see you next time for 9.3, which I believe is our last section. We'll see you next time.